Hello everyone, my name is Miriam Al-Mayan. I just graduated from Georgia Tech with a Master's of Science in High Performance Buildings. Today I'll present to you 3D heat transfer analysis and architectural modeling, a case study with OpenFOAM. First, the problem statement is that popular simulation tools in architecture like Therm and HT-Flux are limited to 2D, leading to inaccuracies in architectural modeling. And the 3D simulation tools are cost prohibitive and not integrated in the modeling software. So the research question is, how can we develop and validate a tool to accurately simulate 3D heat transfer in architectural applications and integrate it into the modeling softwares in architecture? Now moving to the bigger picture. First of all, climate change, because the rate of warming now is 40% higher than the rate in the 1900s. Specifically, the global land temperature, where the places of 8 degrees Celsius in average are now 10 degrees Celsius. And it keeps increasing. We are not maintaining this increase. Then moving to the carbon emissions, the global emissions from the buildings are 59% only from the iron and steel in the built environment. And then 3D heat transfer is critical in building design, such as choosing the orientation or shading of the building. As you can see, here is an example of the max sensible cooling, and then we increased the R value, which reduced the sensible cooling by 34%. After doing the literature review, I summarized the existing tools in a table, which are the 2D and 3D heat transfer tools. As you can see here, the name, the type, overview, and limitations. For example, HT-Flux is a 2D simulation for heat and water vapor transport, but it is cost prohibitive and require additional tools to download, additional to the architectural software. Same with, for example, SimScale for 3D heat transfer. It is cost prohibitive and requires additional tools with limited post-processing options. Now, steps leading to the method. First, I wanted to explore the simplest case of heat transfer, which is a 2D brick wall. We started with number 1, the hand calculation, and we got 10 watts per meter squared for the Q, which is the heat flux. Then number 2 is real-time measurement using U value and heat flux sensors. With the same boundary conditions, we got the same result of heat flux of 10.9 watts per meter squared. Then moving to number 3, which is taking the same case, same brick wall, and boundary condition and modeling it in a 2D heat transfer software, and we also got the heat flux to be 10.9 watts per meter squared. Now we did all of these steps. What about the 3D case? We started with looking for a validation case first, and we found a case validated by the Thermal Bridges in Construction ISO, and also validated in QuickField, and this is the case. We constructed the case with the same materials and layers in Rhino, and then using the user dictionary, we assigned each material and region to the properties used in the validation case. Then moving to Grasshopper, we assigned the properties and wrote the STL files for OpenFOAM, which we will now go to. And then we used the script component to write OpenFOAM text files. After that, we moved to OpenFOAM. First, OpenFOAM is a free open source CFD software, but it is complex because it does not have a user interface, and it's all by the written text files you can see here. Now, running a steady 3D heat transfer case requires three files, which are the zero, constant, and system. Each one of these have all of the regions of our case, and then within the regions there are the temperatures, U and P, and then constant and system. Each of them is responsible for something. For example, constant is responsible for the properties of the materials and so on. And system is for the solver, basically. And as you can see here, this text file was automatically written by the workflow we did here in Grasshopper. And the materials we inputted, such as the temperature, conductivity, density, specific heat capacity, all taken from this case, the validation case, and was run in OpenFOAM. Then the results show an average percentage of error of 0.05%. In the z-axis from z equal 1.2 to z equal 2.2, where you can see the differences of the temperatures, validation case, and the simulation case. And this is a comparison between the OpenFOAM results we had and the quick field results. Then we also took the results and compared it with the real-time experiment. As you can see here, these lines are the readings from the sensors. This is the indoor sensor, and below is the outdoor U value and heat flux sensor. And the lines are the readings. And then the dots correspond to the results from the OpenFOAM simulation that we did. And as you can see here, a minimum percentage of error of about 0.003% and maximum of 0.01%. And according to this case in the ISO, it is considered validated and complies with the results. To conclude, this research presents an automated integration between Grasshopper, Rhino, and OpenFOAM to present thermal performance analysis into architectural design process. Now, the future direction is includes packaging this Grasshopper automation to provide user-friendly Grasshopper plugin, and also develop a holistic interface to simulate for the entire building's heat transfer, and not only a corner or a section or 3D section. Then modifying the solver and workflow to simulate for transient state heat transfer, enclosure performance and analysis, condensation, and mold growth. To conclude, the contributions of this research are quicker OpenFOAM case setup and automated workflow. You can find the workflow here and modify it below and modify it based on your architectural uses and architectural building. Also, architectural integration, because we connected OpenFOAM without the user interface with Rhino and Grasshopper, where we kind of provided a user base to interact with OpenFOAM. And then number 3 is clear 3D thermal analysis and precise post-processing. By using PairView, you can probe any different location and explore more about the 3D anatomy of your building. Number 4 is cost efficiency, because this is an open source workflow and does not cost anything. And as I said, you can find it below. To conclude, I just want to thank my Professor Patrick Kastner for his time and efforts with me. in finishing up this project and hopefully more collaborations in the future. Thank you for your attention. If you have any questions, please email me at this email here. And thank you again.